40 to 180, 190. So if the temperature gets 10 inverse femtobarn and there's no Higgs boson, then we should probably be able to exclude the entire mass range between 0 and 190, 180, 190 GeV. And then, of course, we're going to move on to the LHC, which collides protons with protons. And until the end of 2011, we'll be running at a center of mass energy of 7 TeV and hopes to accumulate an integrated luminosity of 1 inverse femtobarn, and then upgrades to 14 TeV and maybe 25 inverse femtobarn by the end of 2014, and lots more by 2016. We've seen this already. Higgs boson production is very similar to the tevatron. The dominant mode is gluon fusion. And what I wanted to show you is the projections for what you can exclude at the LHC. So let me first show you the plot for the 14 TeV example, which is the design case of the LHC that's been studied a lot. This is for the CMS experiment. So if the mass of the Higgs boson is below 130 GeV, then the decay mode that CMS would use is Higgs to 2 photons. And this gives you the integrated luminosity you need to do a 5 sigma discovery to get a statistically significant signal, greater Higgs boson mass. So you see, in order to get a statistically significant signal up to about 150 GeV or so, you need 30 inverse femtobarn. Here in this particularly sweet spot, you can see it with a little bit more than 10 inverse femtobarn. So about a year of running at design. That's about a year of running at design parameters. If the Higgs boson is more massive, then the WW decay mode will be dominant, and that gives you this kind of exclusion. So again, if it's near 160 GeV in its mass, then you can see it with even less, much less than an inverse femtobarn. If it's lighter, then you have more background, and if it's more massive, then you lose rate, and you need more data to exclude it, to see it. Right. Now, if the mass goes above 190 GeV, up to about a half a TeV, then the decay mode into 2 Z's will be the dominant one, and that's very easy to see. Both Z's can decay to leptons. It's a very characteristic signature. It's very easy. It's relatively little background, and you can see that very nicely as a striking signal in the detector. And if it's even more massive, then you again go back to the WW decay mode, but you also look for hadronically decaying W's in order to get more data. And with all this combined, you should be able to see the Higgs over the entire mass range from about 100 to 800 GeV with a little over 10 inverse femtobarn. So that was what the LHC was designed to do. Of course, one remark that's interesting, I think, is this little curve here would tell you how much integrated luminosity you would need to see the dominant decay mode of the Higgs boson to BB bar at low mass. And you would need at least 20 inverse femtobarn at design. So you need about a year of running at design luminosity to see that decay mode at the LHC. So this is the decay mode that the tevatron is trying to use. And it's much harder to see at the LHC because the background from top decays is much larger at the LHC compared to the tevatron. And here's another example where the experimental program was driven by the search for the Higgs boson, the CMS experiment, which you see here, and this is a person, and it's a technical marvel, and one piece of it, namely the calorimeter that was supposed to measure the energy of photons coming from these collisions, is a homogeneous electromagnetic calorimeter made of 78,000 tungstate crystals to get an excellent photon energy resolution to be able to see the mass peak from a Higgs to photon decay. Okay, what can the LHC do in the next couple of years when the energy will be 7 TeV and maybe an inverse femtobarn will be accumulated? So these are very recent results of projections from CMS. And you can see here again the ratio of the 95% confidence level limit to the standard model cross-section, the expected limit. to the standard model cross-section, and where the line goes below 1, that's the mass that you can exclude, and you see it's about 145 to 190 GeV that CMS would be able to exclude over the next 2 years. And this is using these 3 decay modes. From Atlas, I don't quite have a comparable plot. They haven't released those yet, but they have this plot here where they look for the Higgs to WW decay mode, and this is the square root. This is the sum of mass energy, so 7 TeV would be here. This is the significance of a signal that they could see with 1 inverse femtobarn data, and these lines are for different Higgs boson masses. And with 7 TeV, you can't discover any of these mass ranges at 5 sigma. The summary. Well, the search for Jerry's boson has shaped particle physics experiment for the last 3 decades or so, but it still eludes detection, and the quest still goes on. Congratulations.
Any questions?